Hello, everyone. Let me just quickly check my audio levels, and looks pretty good. Okay, so uh, what we're going to do today is I'm just going to do a couple of questions on energy. One question, which is like one of my roller coaster questions with a spring, and another question on the energy for a harmonic oscillator, simple harmonic oscillator. Okay, we'll also do a live chat both on Monday and Wednesday of next week, and that's in anticipation of your test on Friday. Okay, so there's no new material. The test will cover only the stuff on Newton's laws. And then there was that short section, which was both Newton's laws and Kepler's laws on Newton's universal law, on planetary motion, and then the energy, and that's what will be on the test. I haven't written it yet. I'll write it on over the weekend, and so by Monday I'll be able to give you more information. The usual question is like how many questions are on it. I don't know. I never think in terms of the number of questions. I think in terms of the amount of time it takes you to do a test, and so I'll make sure that it's doable within 1 hour. Okay, so well, let's just start. Oops, you know what I forgot? I forgot to turn on my other whiteboard. That's okay. That'll happen in the background while we start the question here. Okay, so the first question is we have a cart and it has a mass of 150 kilograms, and I place it at rest against a large spring with a spring constant of 17 kilonewtons per meter. Okay, and that's point A. Okay, and the spring is compressed by 1.5 meters. So you can imagine, I'll draw this in a minute, but you can imagine a spring which has been compressed and the car sitting up against that spring. And the car's not moving yet and the spring's not moving yet until I guess I release it. And then what's going to happen? When released, the spring is going to push the cart forward. Okay, well, then the cart's going to be moving. Eventually the spring will have sprung. It'll give up all its energy to the cart, and the cart will travel some distance along a flat hill top. Okay, and I call that point B. And then the cart goes downhill to ground level, and I call that point C. And the vertical drop in going from the top of the hill to the bottom of the hill is going to be 15 meters. And to start, we're going to assume no friction, and we're going to take h equals 0 ground level. And you'll see why it's important for me to tell you that. On the test, I'll say h equals, ground level is h equals 0. I'll make sure it's very well defined where h equals 0 is, because you're going to need that to make sure that you get the same answers I do. Okay, and then there's a bunch of questions on energies and velocities. All right, let's switch to the whiteboard here, and it's not showing up. Oh, there it is. Took a sec. Okay, and so let's draw the picture. Now, you don't have to be super accurate with these pictures. Like, you don't need a coordinate system the way you do with, like you did with kinematics, but you do need to have enough information that you can assess where all the energies are at each different point. So here's the top of the hill, and then the car goes downhill like that, down here like that. And at the top here, there is a spring, so I guess the spring is braced by a wall. Here's my spring. Oh, this is a terrible picture, but I think you got the idea. And it's pushing up against the car like this. Okay. and the car is going to go forward and then go downhill. And I said there's 3 points. There's the point at which the car is up against the compressed spring like this. And then after the spring has sprung, it's over there. And then also I'm interested down here. And I call this point A, this point B, and that point C like that. Okay, and I tell you that ground level is down here. Well, that is ground level, and that's H equals 0. Okay, that's where we're going to take H equals 0. All right, and you're going to need that because you're going to be calculating the potential energy due to gravity, mgh, and I think you could see that, potential energy due to gravity is going to be 0 at point C. But if I had chosen, I'll erase this in a second, but if I had chosen H equals 0 up here, okay, suppose I said take H equals 0 at the top of the hill, well then mgh would not be 0 down here. Mgh would be 0 up here, and you get a different answer. Now, if you did the problem, you'd still get the same results, but you know how I break down my questions into parts? The intermediate parts would be different. So I'm going to tell you where H equals 0 is on the test, and I told you in this question too. Okay, let me erase that. All right, and there it is. There's the situation. Now, before we jump into the problems, I said you really need to assess where the energy is in each of these at each of these points. Okay, so the total energy is the same. So question A, I'm going to say, what's the energy at A, B, and C? Well, the answer is the same for all of them. Okay, so that's the whole point of conservation of energy. If you can calculate the conservation of energy at one point, you have it at every point. Okay, so at the top here, you might say to yourself, well, where's the energy there? Okay, so there's a total, but like it's in different forms. So where's the energy? And generally there's 2 places. There's the kinetic energy, and kinetic energy is just the energy because something is moving, and that is always calculated using the formula 1/2 mv squared, like that. Okay, check if everything is working here. Yeah, okay, so 1/2 mv squared. And then there's a potential energy, and the potential energy is a little different because the potential energy can come from a lot of different sources. Okay, so the kinetic energy, it can only come from things that are moving. Now, right now, we only know about linear motion. Later in the course, it's actually our last topic. We'll be talking about rotational motion. So even when things are rotating, they'll have a kinetic energy, but they have to be moving to have a kinetic energy. And so the car up at the top here, it's not moving. It won't have a kinetic energy. The potential energy can have multiple sources. Okay, now you only know about 2. There's potential energy due to height, okay, due to gravity, that is its height, and then there's a potential energy due to a spring, okay? And so there's 2 pieces that go into this potential energy. One of them is potential energy due to gravity, and that's given by the formula mgh, all right? And then there's a potential energy due to the spring, and that's 1/2 kx squared, like that, all right? Okay, so at the very top here, at point A, before the spring pushes the thing, the velocity is 0, and so there'll be no kinetic energy up there. Okay, and then you say, well, is it at ground level? Well, no, because it's at a certain height. It's actually at 15 meters height, like that. So it does have a gravitational potential energy. And then you say, well, is the spring compressed? Is there any energy in the compression of the spring? And the answer is yes. And so at point A, the total energy is obtained by adding mgh plus 1/2 kv squared. Okay, now let me erase those. Okay, and then at point B, you can ask the same question. All right, now the total energy, whatever that number turns out to be, I forget right now, but whatever that number turns out to be, it'll be the same number, but the where it's distributed will be different. At point B, the car will be moving, so there'll be a kinetic energy. The car is still at the top of the hill, so there'll be a potential energy due to gravity, but now the spring has sprung. Okay, it's already given up its energy, and there won't be any energy due to the spring. Okay, and so you could see how that energy has been sloshed around. It's been changed, all right? And then finally, let me erase all those. Down here at point C, actually, get rid of that too. At point C down here, all right, you could say, well, where's the energy? Well, the spring is out of the picture, so there's no potential energy due to the spring. It's at ground level now, so there's no potential energy due to gravity. It's due to being up at some height, but there is going to be a kinetic energy like that, okay? And so again, the number's the same at point A, B, and C, but the distribution of the energy between those three is going to change, okay? So just keep that in mind because that's how we're going to solve the problem. All right, so let me switch back to my whiteboard here, okay, and see if there's any questions in the chat. Good, 7 people listening, and everything looks good. All right, so that's the way to think about these problems, all right? So the first question is, what is the total energy of the system at point A, B, and C? And you say, did I give you enough information at any of those points to calculate the total energy? And the answer is yes, I gave you enough information at point A, okay? And so I'm just going to cut and paste my answers here. I hope I don't go too fast. If I go too fast, because you might be writing this down, just tell me that I'm going too fast. But I like the copy and paste method because I tend not to make as many errors. That's all, okay? But I'll go through all the steps here, okay? So, as I said earlier, the energy is a combination of kinetic and potential, all right? And the kinetic, there's only one way to write the kinetic energy, and it's this way here. The potential, however, can have multiple contributions, and you guys only know about gravity and a spring. Next semester we'll do electricity, so there'll be even a potential energy due to electricity, okay? And the potential energy due to gravity is given by that, and the potential energy due to a spring is given by 1/2 kx squared. Okay, and you say, like if you look at points B and C, you would say, oh, he didn't give me enough information there. Like you don't know the velocity at C, so you can't really use C because these two are 0 at C. So you say, well, maybe I could use this, just that at point C, but nah, you don't know V, so you can't calculate it. But if you think about it, at point A, I give you all the information you need, okay? And so at point A, you say, well, okay, what's the kinetic energy at point A? It's not moving when it's squished up against the spring. So just imagine that the spring is compressed and the car is just sitting there waiting for someone to like pull a trigger, and it's just sitting there, but it's not moving. And if it's not moving, the velocity is 0. And if the velocity is 0, the kinetic energy is 0. Okay? mgh, well, the mass I tell you is 150 kilograms, so there's the mass. G, technically 9.8, but being lazy in the course a little bit, and we've been always rounding it off to 10, so we'll continue rounding it off to 10. Okay, and then h is the height of the hill, and that's 15 meters. Okay, so it's at a height of 15 meters, and so h is 15 meters like that. Okay, and again, you can see why I have to tell you where h equals 0 is, because if I'd said that the top of the hill was h equals 0, then that would have been 0. Okay, and then ground level would have actually been negative 15 meters. All right, but we're doing it this way. So there's the potential energy due to gravity, and then the potential energy due to the spring, a half. K, I gave you K as 17 kilonewtons per meter. Okay, kilonewtons is not MKS, but just remember kilo is just 1,000. So you could say 17 kilonewtons, or you could say 17,000 newtons. It's exactly the same thing. All right, and so over here that's 17,000 newtons. Now you'll see in the assignment and on the test, and even when I do the problem today, I'm going to be working with kilojoules an awful lot instead of joules. The MKS unit is joules, but we're going to use kilojoules a lot, and that's because a joule is very small, and so typically you get values that are into the kilojoules range, like food energy. In the United States, we measure food energy in calories. So if you get a chocolate bar or something, you look at the back, it says 300 calories. That's the food energy in that chocolate bar. Okay, but in Canada and in Europe, it's actually measured in kilojoules. All right, and I forget the conversion, but it's roughly the same. It's like in the hundreds range or something like that. So a chocolate bar in Europe might be like 100 kilojoules or something like that. And so it's good to know that, because especially if you're going into one of the life sciences like ESS or PT, or you guys are probably biology majors or chemistry majors, you're going to work with kilojoules quite a bit. So kilojoules, kilonewtons, and so on. Be careful with those. The MKS unit, as I said, is actually newtons, and so we have to convert the 17 kilonewtons to 17,000 newtons. And then X, I tell you, X is the how much the spring is compressed, and I tell you that's 1.5 meters. Okay, so there is the equation for energy at all 3 points. Okay, but here is the energy with the number substituted at point A, because you have all those numbers there, and there's the kinetic. There's the gravitational. There's the spring, and it turns out to be 41,625 joules. and that turns out to be 41.625 kilojoules. Okay, and that is the energy at point A, point B, and point C. And energy is conserved here because there's no dissipative forces, there's no non-conservative forces, and and there's only one that you know of that makes energy become heat, and that's friction. So no friction, energy is going to be the same at all 3 points. Okay, so there's the first one. Let me see if there's any questions so far. No, it looks good. All right. Okay, so now what's the velocity at point B? So, well, let me see. It doesn't take long. Let me switch back here just to remind you. Point B, you're still at the top of the hill. The spring has sprung, so the spring has given up its energy, but you're, still at the top of the hill. Okay, so you still have that potential energy due to gravity. You still have H equals 15 there. All right, and so how do you do that? Well, the formula, you could still start with that formula there. Whoops, that formula there. Okay, and let me just cut and paste here, and all right, you could still start with that formula there. All right, but now just be aware that the spring has sprung, so to speak, and so x is equal to 0. Okay, x is how much the spring is compressed, and if the spring has given up its energy, it's not compressed anymore. X is equal to 0. Okay, but we're still at the top of the hill, as I just said, so h is still 15 meters, and so the only part of it that goes away is the 1/2 kx squared. This part now is 0. Here, like that. That's 0. Okay, and so you still have the 1/2 mv squared because you got a kinetic energy. No, I shouldn't say you still have it. Now you have a kinetic energy, 1/2 mv squared. Okay, and you have still a potential energy mgh. All right, and so we were asked to find the velocity, and so when you go to substitute into this, you're going to find that you don't know v, of course, because that's what you're trying to find, v. And you say, well, do I know the energy? Yes, you do, because that's the point of question A. The energy at A, B, and C is the same, and so you know what that energy is. It's the 41,625 joules, okay? And so you can substitute in for E, you can substitute in for M, you can't substitute in for V, but that's what we're solving for anyhow. Okay, and the MGH is 150 times 10 times 15, like that. Okay, and so just solve for V in that. All right, and so I'll go over those details quickly because this is kind of easy. 0.5 times 150 is 75, and that works out to 22,500 joules. And then subtract that from both sides, divide by 75, take the square root, and you get that long number there. And on a test, you would see it rounded off to 3 significant figures, and because that's what we've been doing in the course, and so that's going to be 16 meters per second. Okay, so at the top of the hill, you have a velocity of 16 meters per second. Okay, now what's the velocity at point C? Not misspelt that. Hold on, let me fix that. Point C. Okay, so what's the velocity at point C? Let me remind you, point C, you're at the bottom of the hill here. Okay, you're at the bottom of the hill, and at point C, all the energy is going to be kinetic. Why? Well, the spring is out of the picture. You're no longer at the top of the hill. You're at ground level, and so there's no potential energy due to either the spring or the height of the hill, your height, potential energy due to gravity. And so all of that energy must have now sloshed into kinetic energy. Okay? And so how do you do that? Well, give me a sec to cut and paste here. You can once again start with that formula there, but now you say, well, what's H? H is 0. What's X? X is 0. So X and H are both 0. And so all the potential energy goes away, and you're just left with 1/2 mv squared. So all of the energy is equal to 1/2 mv squared. All right. And E, because it's the same all the way through. That's 41,625 joules, and that's got to equal 1/2 m. So there's 1/2 m times V. And if you solve for V, you get 23.55844 meters per second, and rounds off to 23.6. Okay, so at this point you can ask yourself the question, do the numbers make sense? You can compare, say, the velocity at the top of the hill after the spring, 16 meters per second, and at the bottom of the hill. And of course, after you've gone downhill, you expect it to be going faster. You expect this cart to be going faster, and it is. And so, that's not a guarantee that you did the right thing, but at least it gives you an indication that you didn't do something wrong. I mean, if you've gotten a number less than 16, you know that you've done something wrong. And my tests are multiple choice, so I always have an answers, or one or two answers which are completely absurd. So like if you know from part B that it has to be bigger than 16, then one of my answers might be like 8 meters per second. Well, you could immediately discount that because it's not physically possible. You go downhill, you're going to speed up, not slow down. Okay, and I think that makes intuitive sense. All right, so far we've done a problem without any friction. Okay, and the next one is, well, let's assume there's friction. So I say, okay, assume there is friction. If the cart is found to have half the velocity at point C, how much energy was lost due to friction? So half of the, well, let me cut and paste the answer first, and then I'll talk you through it. Okay. So half of the velocity, so half of the 23.6 is, and I did something funny here. I kept all the decimals. The reason I did that, and you might want to even do that on your test, is because if you round off and then you use the round off number again, and then you round off again, and then you round off again, every time you round off, you add a little bit of error. So I tend to keep too many digits, or I keep all the digits that my calculator can handle as I go through the various steps. But then when I compare it to my answer, I will round it off. Okay, so so I really didn't do half of 23.6 there. I really did half of 23.5584. Okay, and that turns out to be 11.77922, like that. Okay, or rounding off 11.8. So you can imagine you did this experiment. Okay, so you've got all the measurements, and you say, I predict that the cart is going to be traveling at 23.6 meters per second when it gets to the bottom of the hill. And you do the experiment and you measure the velocity and you find that it isn't. It's only 11.8, and you go, well, why is the velocity here 11.8 and not 23.6? And that's because there was friction. Okay, and what friction does is it makes energy, the kind of energy that you know of, it's sometimes called mechanical energy. It converts that mechanical energy to heat. Now, heat is a kind of energy, but we haven't really studied it. That's we'll study it next semester. Okay. As far as you're concerned now, heat is just making energy go away. In fact, people say, the energy was lost to heat. Okay. We put that in quotes because it's not really lost. It's just if you don't know about heat, it looks like it's lost. Okay, but it is. It's like your car keys, right? Did you lose your car keys or did you just misplace them? Okay, so it's just that the energy gets misplaced as heat, and if you don't know about the heat, it looks like it was lost. And historically, until Joule, actually, Charles Joule is the guy who discovered heat was energy. So until Joule, people were confused. They said, well, is energy really conserved? It's supposed to be, but we don't see that it is. So what's happening? And Joule actually explained what was going on. He said, no, it's there. It's just it's heat. Okay. He sort of found the car keys. Okay. Okay. So anyhow, a bit of an aside, but just it's important to understand what friction's really doing. Okay. So you do the experiment and you find that you get only half of the velocity down there, and you go, well, okay, so how much energy was lost to friction, lost to heat because of friction? And if you go back to the picture here, okay, the energy at point C, it's still all kinetic energy. There's just less of it, but it's still all kinetic energy down here. Okay, and the distribution of the energies are still the same. At each of those, there's just less of them, less energy, because the friction has dissipated some of it away. Okay, and so when you go to use the formula, you can once again use the formula E is equal to 1/2 mv squared, because all the energy down there is kinetic. Okay, there's no potential energy due to gravity, there's no potential energy due to the spring. Okay, at this point you don't know what E is, okay, because it isn't conserved the way it was previously, because it was dissipated by friction. Okay, and so you use the value of the velocity that you just got. Okay, and I used all the decimals there so that we didn't have a round off error. Okay, and it turns out that at the bottom at point C, you're only going to have 10,406 joules, or 10.4 kilojoules. Okay, so in the previous problem, you had like 41.6 kilojoules, and now you only have 10.4 kilojoules. Where did that other energy go? Heat. Okay, and so what was that energy? Well, you do a delta E, that is a change in the energy. And you say, okay, how do I do that? Well, whenever you do a delta, it's like the energy after, the after minus the before value. So it's the energy after, or here EF, the final energy, minus the initial energy. So the final energy was 10,406 minus the initial energy, 41,625, and that gives you negative 31,219. Okay, joules. All right. Now negative because it's lost. Okay, because it's a decrease in energy. All right. So that's the energy that was lost due to heat. The mechanical energy, the energy that you could see because things are moving or because of potential energy, that is less now by 31,000. The heat, if you could measure it, and we'll talk about how to measure heat next semester, that has now increased by 31,219 joules. Okay. All right. So part E. If the cart traveled a full distance of 500 meters, and I'll draw what that means in a second, what was the average force of friction along the path? Okay, so let me switch back to the diagram to show you what I mean by that 500 meters. So the cart is traveling. Let's do this in red. The cart is traveling, and all along the path here that it travels, no matter how curved it is, it's experiencing friction. So think of that red line as friction, 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 all the way along there. If you were to measure that curved path, okay, I know that the drop here, the drop is only 15 meters, but I don't tell you how far you're traveling this way or how far you're traveling that way. Okay, so this is 15 meters, but I do tell you that that full curved red path there, okay, with friction, that's 500 meters. So all the way along that curved path there, the cart is experiencing friction, and it's experiencing friction over a distance of 500 meters, half a kilometer. Okay, and so how do you do that? How do you get the friction out of energy information? So, I went through some theory, in the pre-recorded lecture, and I gave you this work energy theorem. And you go, well, you never really use this work energy theorem. What is it about? So the work energy theorem is actually more general than conservation of energy. As you can see, if there's friction, energy is not conserved, but the work energy theorem still applies. And what the work energy theorem is all about, really, is it relates energies and forces. Okay, or actually, it equates energies and work is defined in terms of forces, to be more precise. Okay, and so if you go back to the definition of the work due to a force, the work due to a force was the force multiplied by the distance over which that force acted, multiplied by the angle between the two forces. So there's a couple of vectors here with my fingers. If my thumb here is like the force, and my finger here, or maybe my thumb is like the displacement, so like a box moves along there, and my finger here, my index finger is like the force, and then there's an angle in there, okay, theta. The work due to that is going to be the force times the distance times the cosine of the angle. That's the definition of work. Okay, now with friction, it always turns out that if something is displaced in one direction, the force is always in the opposite direction. So displacement one way, force the other way. Okay, so 180 degrees between. Okay, so cosine of 180 degrees is negative. And so the work due to friction is given by this formula right here. Cut and paste this. It's given by that formula right there. Now that's not work in general, but that's work due to friction because the angle is 180 degrees. So the work due to friction, which I've written as a WF, is going to be the force of friction times the distance over which it acted, multiplied by the cosine of 180 degrees, and guess what the cosine of 180 degrees is equal to? -1. Okay, and so the work due to friction is given by that right there. All right, and so why do you need this? Well, it kind of comes into play with the work energy theorem, because guess what? That delta E, according to the work energy theorem, that delta E is WF. Okay, it is WF. All right, and so I didn't bother even writing that. I just took the value of delta E here, and I put that in for WF right there. Okay. And what's that got to equal? Well, that's got to equal minus FF, and we don't know FF because, after all, that's what we're trying to calculate, multiplied by D. But I tell you that D is half a kilometer, 500 meters. And so there you go. Plugging into that, you have this. All right. And then dividing both sides. Notice the negative signs will cancel, okay, because they have to. All right. The energy is lost, and that's lost because of work due to friction, and work due to friction is always negative. Okay, and so you just divide both sides by 500 and you get 62.4 newtons. Okay, I said average because I don't know. I mean, like, who's to say that the friction is exactly the same all the way along? Okay, but it might have been a little bit more at one place, a little bit less on another place, but on average it had to be 62.4, because 62.4 multiplied by that 500 meters is going to give you the 31,219 joules, which was lost to heat. Okay, so there you go. There's our first example. This is an example. It's kind of like our roller coaster, but it's I don't know, a go-kart or something like that, and it's being pushed by a spring. Okay, now there's lots of variations on these kinds of problems. Okay, like your assignment is a variation, but you can get pretty creative with these. And so I'm going to show you another one. We're not actually going to solve it. I'm just going to kind of set it up for you so that you can think about it. And before I do that, let me see if there's any questions in the chat. Oh, everyone looks good. All right, so let me switch to the whiteboard, and let me create a new whiteboard here. All right, so here's a kind of a creative problem. We have, let's do this in black. We have ground level here like this, and we have a spring like this, and there it is, and it's compressed. I guess it's got a platform on top like that. Okay, and I put a box on top of this platform like this, and I compress my spring a distance x. Okay, so I've compressed my spring a distance x. So what's going to happen when I let go of my spring? Well, the mass here is going to go boink. It's going to go up into the air here like that. It's going to go up a distance h like that. And here it is up in the air. All right. And I want to know its maximum height. Okay, I guess I got to tell you m. So I'm not going to put numbers on this, but you can imagine that I give you x. I guess I got to give you k too. So I give you x and k. I give you the mass, and I ask you to calculate the height. I say, well, how high in the air does it go until it gets to maximum height? Okay. And so how would you do this problem? Well, if you had to use Newton's laws here, this one would drive you crazy, okay? Because there's all sorts of stuff going on, all right? So, that's why energy is nice, because it makes a problem like this really simple. And down here, at this point right here, let's do this in red, I guess. At this point right here, the spring is compressed. It's ready to fire that mass, but it's not moving yet, just like our car. And so here you could say the velocity is 0. And so guess what? Your kinetic energy is 0. That was easy enough. All right, kinetic energy is 0. Now I didn't tell you where the height, where the ground level is. Let's not put ground level down here. Let's put h equals 0. I guess at the bottom. Let's put it. Whoa! What did I just do? Undo. There we go. There we go. Let's put h equals 0 right there. Oh, I know what I did. I switched the layers. Okay. Let's put h equals 0 right there, okay, at the bottom of the mass there like that, okay? Well, if h is equal to 0 there, then guess what your potential energy due to gravity is? Your potential energy due to gravity is 0, okay? So all of the energy down here is due to 1/2 k x squared. That's it. That's all your energy down here. Okay, and that's easy to calculate because in principle I've given you x and I've given you k. Hold on, this square here looks awful. There we go. All right, that's the energy right there. Okay, and then you say, well, what about up here? Well, up there, guess what? It's at maximum height, so the velocity is 0, right? Okay, well, and so the kinetic energy is 0, obviously. All right, the spring has sprung, and so x is equal to 0, and so that 1/2 kx squared, that's also 0. All right, and all of the energy is mgh. It's all mgh there. Okay, and so guess what? to solve this problem, all you have to do is equate this to that one down there. Okay, and problem solved. All right, so it's actually pretty trivial. All right, but if you had to worry about the details of the dynamics all the way along here, like at all times between the initial condition down here, I guess this is our initial and that's our final condition up here. Like if you had to worry about all the dynamics, you might say, well, what's going on right there? Well, at this point, it might have some velocity. Okay, it may not have, lifted off the spring yet, and so the spring might still have some energy in it. And it's no longer at zero height, so there might be some height there like that. And so guess what? You've got energy distributed between kinetic energy, potential energy due to the spring, and potential energy due to the height. I mean, that the motion at this point, the dynamics right at that point right there, that's pretty complicated. And the dynamics as you go up here at all the points along there are pretty complicated. But if all you're worried about is this initial and that final, the problem becomes extremely easy. Okay, well, I don't know about extremely easy, but it becomes very easy. Okay, so I don't have to solve this, but I think you can see how conservation of energy is useful in making this problem a very simple and easy to solve problem. Okay, so all I'm trying to show you is that like this formula right here, you know, uh, which uh, at least for the problems we've been doing so far in the course, not the ones next semester because there'll be more potential energies, but at least for so far, that formula right there, you can use it in pretty creative ways. Okay, so there's another example of firing a mass up into the sky. Okay, all right. So let me see if there's any questions in the chat here. Everyone looks good. All right. Well, you know what? Let's do question number 2. So question number 2 is a harmonic oscillator. Okay. And we did do harmonic oscillators, for kinematics. And, I'm not going to retest you on kinematics, as I said in the syllabus, but, you can't mind up kinematics. Some of the stuff from the kinematics comes over into all of the sections, okay? So, not by design, but just by necessity, the course is cumulative because physics is cumulative. It's like math, it builds concepts build on top of one another. You can't pull out the foundations without having the whole thing fall apart. So don't mind up all your kinematics. Okay, you're still going to need it for a while. So but now we added something more to the oscillator beyond its kinematics, and that is its dynamics. Okay, and one of the things that in that one pre-recorded lecture that came out is that whenever you have an oscillator, it's like the oscillator has to be driven by some force. That force is basically like a spring. Okay, it's not necessarily a spring, but it's like a spring in that it has a spring constant. Okay, now let me describe that. You got these little cilia in your ears. They're tiny little fibers which vibrate back and forth, and then they stimulate some nerve, and that's how you can hear. That's how you're hearing me right now. Okay, and so they have they don't you if you looked at them, you wouldn't see a spring there, but they have a rigidity to them. The fibers have a rigidity, and it's that rigidity that controls just how much it vibrates back and forth. If they were infinitely rigid, in other words, if K, the spring constant, were infinite, they wouldn't vibrate, and that'd be pretty useless. Okay, so K, I know we call it a spring constant, but even if you don't see a physical spring in there, think of that spring constant as kind of a measure of the rigidity of whatever's oscillating. Okay, and then I mean, like you say, on a lot of my problems, I say oscillator, and you say, well, what's an oscillator? Well, it's generic. I mean, it could be those little cilia in your ears, or they could be a skyscraper. Okay, even skyscrapers, they'll oscillate back and forth. Okay, and if you've ever gone on top of a really high building, you feel that it's moving a little bit, and it's a little bit disconcerting. Go, geez, what's this thing doing? It's oscillating, believe it or not. And you just hope that the engineers knew what they were doing, and they took into consideration the oscillations, and it won't come down. But there are actually YouTube videos, movies of bridges that have fallen apart because they began oscillating a little bit more than the engineers had anticipated, and they broke. Okay, I wouldn't be afraid of going up on top of a building, but they oscillate too. And so you say, well, I don't see a spring there. I know. Again, it's the same thing. There's a certain rigidity, and whatever that rigidity is, we just simply call it a spring constant. Okay. All right. So that's one thing that came out of this, and the other thing is for a simple harmonic oscillator, there's no friction, and so the energy is a combination of the kinetic energy and the spring potential energy. Okay, again, no spring, but there's still a rigidity K. Okay, so there's a spring constant there, and so for the kinetic energy, 1/2 mv squared, and for the potential energy, 1/2 kx squared. Okay, and using that, we can solve these problems here. Okay, so let's start off here. An oscillator of mass 150 grams, have to convert that to kilograms, is found to have a period of 0.37 seconds. Remember what a period is? If the oscillator starts at one end, okay, and it travels all the way to the other end and then back again to the beginning, the time it took to make that complete cycle, that's called a period. Okay, so 0.37 seconds. And also I tell you that when it is 2.5 centimeters from the origin is also equilibrium. So if my finger is equilibrium, the oscillator, remember, it moves, it oscillates symmetrically about the origin. Okay, so when this thing is 2.5 centimeters, that distance there, 2.5 centimeters from the origin, it's found to have a velocity of 0.5 meter per second. Okay, and I didn't tell you whether it was 0.5 meter per second inwards or outwards. It doesn't matter because it's going to pass that 2.5 centimeter point twice, once on the way in and another one way on the way out. And when it passes the 2.5 centimeter point, both times it'll have the same velocity, just a different direction. Okay, it's, remember, like when we threw a rock up into the air, when it passes the same height, it has the same velocity up, and then it comes down, it has the same velocity down. It's the same thing with the oscillator. When it passes that 2.5 centimeter mark, whether it's going in towards equilibrium or out away from equilibrium, it's going to pass that point with 0.5 meters per second. Okay, 0.5 meters per second. All right, so the first question is, what's the angular frequency? Okay, so angular frequency comes up over and over and over again. Even if I don't ask for it in a question, solve for it because you're going to need it. Okay, and here's the angular frequency. It's given the symbol omega, which looks like that W. All right, like that. All right, so that you know, omega, last letter of the Greek alphabet. That's angular frequency, and it's measured in hertz or per second, and it's equal to 2 pi divided by the period, capital T. And so just plug in 2 pi is 3.14. The period, I tell you, is 0.37 seconds, and that's going to give you 17.0 hertz, or equivalently 17 per second. Okay. All right, well, that answers the first one, and just to, sometimes I lead you on in, the questions so that I show you the steps, but, if I don't, you might still have to just calculate omega, realize that you're going to need omega for the next steps, okay? So what is the spring constant? Okay, and go, whoa, how do I get a spring constant out of this? Well, you have to know that from the dynamics, okay, and for the calc people like you guys, I actually proved this, that there's a relationship between omega, the mass, and the spring constant. Okay, so omega, k, and m are related to one another, and here's the formula. Okay, I hope I'm not going too fast, guys, for you if you're writing this down. Okay, so just don't be afraid to say to me in the chat, slow down if I'm going too fast. Okay, so anyhow, there's the formula that relates omega, k, and m. Okay, and what are we solving for? We're actually solving for the spring constant k. So I'm just going to rearrange it and isolate k first. So squaring both sides, I get omega squared is k over m, and then multiply both sides by m, I get k is equal to m times omega squared. Okay, and then substitute in for m. I gave you 150 grams. You got to convert it to kilograms. It's 0.15 kilograms. Okay, so there's your mass. And omega, we just calculated that. It was 17.0, like that. So 17.0 squared. And that turns out to be 43. And the MKS units for the spring constant are newtons per meter. Okay, it's basically how much force do you need to compress this thing by some unit distance. Okay, and if you think about that, that is kind of like what you mean by a rigidity. It's like, if I push so hard, how much does it deform? How much does it move? If I push harder, how much more does it move? If I push harder, how much more does it move? Okay, so how much does it move? That's or how much force does it take to move it? For 1 meter, or to compress it 1 meter. Okay, anyhow, so K is equal to 43.35 newtons per meter. Okay, what's the total energy of the system? So now for that one, of course, energy is always given by the sum of the kinetic and the potential. But in this case, we've got the oscillator this way. There's no real gravitational potential energy. Okay, and so it's all either kinetic energy or potential energy due to the spring. Okay, and so here's the formula. It looks like, again, it looks like the one we had above, but no MGH. All right, so 1 half mv squared plus 1 half kx squared. Okay, and what's the total energy? And you say, well, did I give you enough information for the energy? Well, yeah, I did. Let's look here what I gave you. I told you that when it's at x equals 2.5 centimeters, v is 0.5 meters per second. Now, there's a lot of ways that I can tell you the energy. I can tell you the energy by giving you the amplitude, okay, and that's actually one of the questions, the next question. And that's because when it's at its maximum displacement, the velocity is zero, right? Amplitude means maximum displacement. X is equal to a, that's your amplitude. And that means that there's no velocity there. That means there's no kinetic energy. It's all potential. At the endpoints, the energy is all potential. In the middle, there's no x because there's no displacement from equilibrium. That's what equilibrium means. It's like the point from which you're measuring the displacement. So there's no displacement. If there's no displacement, x is equal to zero. There's no potential energy. All the energy is kinetic. And so in the oscillator, it goes from all potential to all kinetic to all potential to all kinetic to all potential and back and forth like that. Here, I didn't tell you what the energy was at the endpoints. I didn't tell you where the endpoints are, give you enough information to calculate the energy at the endpoints. I didn't give you enough information to calculate the energy at equilibrium. I told you some like generic point, and that is 2.5 centimeters from equilibrium has a velocity of 0.5 meters per second. Okay, and here's the thing about conservation of energy. If you can calculate the energy anywhere, that's the energy everywhere. Okay, so I gave you enough information to calculate the energy at one point, and that's going to be the same energy everywhere in the cycle of the oscillator. All right, so let's go back here, and energy is kinetic plus potential. In this case, that's all there is. There's just a 1 half mv squared for kinetic and 1 half kx squared for potential. Plugging in those numbers, we have a half. The mass was 0.15 kilograms, and the velocity at that point is 0.5 meters per second. Okay, and then square it. And then for the potential energy, it's 1 half. K we just found at 43.5, and X is 2.5 centimeters, but you got to convert that to meters, so it's 0.025 centimeters. Okay, square that, and then you just calculate it, and you get this energy here. Okay, that number there. It's actually very little energy. This oscillator is, a weak, very weak oscillator, but you can have that. All right. So there you go. So that tells you the energy, the total energy of the system. Then I say, what about the amplitude? Okay. And for the amplitude, you go, well, is there a relationship between the energy and the amplitude? I kind of answered that a minute ago. Yeah. Because when x is equal to a, all right. So what do I mean by x is equal to a? Well, here, if it's just a potential energy, you'd have that, okay? But when x, that's only, when x is equal to a, because at x equals a, v is 0. And what happens is this formula right here, because x is 0, no, not, sorry, because v is 0, that's 0, and it goes away, and this is the only term that remains. But that only happens when x is equal to a at the endpoint, and so there's your formula, okay? So I hope I didn't go too fast there, but basically when you're at maximum displacement, x is equal to a, v is 0, and all you have is a potential energy, okay? But like I said a minute ago, if you have the energy anywhere, you have the energy everywhere. And so we know E. The only thing that's unknown here is A, and we can solve for A. Okay, so I rearranged it first and isolated A rather than plugging in the numbers. I mean, I kind of like doing that, although students tend to like doing it the other way. I mean, whatever works for you is fine, but you do know E. You do know the value of E. But like I said, I rearranged it, so I multiply both sides by E. I multiply both sides by 2, and then divide by K, and I got this next formula here. And then I took the square root, and that gives me that A is equal to the square root of 2E divided by K. Substitute in for E. E is this number up here, and K is 43 point, you know what, maybe I should actually do it so you can see what I did here. Let me see here. There we go. So for E, I substituted in this number right here. And for K, I substituted in this number right here. Okay. and that gives me this answer there in meters. But since we've been working in centimeters, I converted it to centimeters. 3.86 centimeters. Okay, does that make sense? Well, think about it. When it got to the 2.5 centimeter point, it still had some velocity. So it's probably going to go past the 2.5 centimeter point. We don't know how much further than the 2.5 centimeter point it'll go, but it'll go further than it. And so you expect this answer here to be bigger than 2.5. And it is. It's 3.86. Okay. Again, that's just a check. It's not going to tell you what the answer is. But if you had gotten an answer here of like say 1.5, then you go, wait a sec. It can't be less than 2.5. It has to be bigger than 2.5. And you'd look to see where you made your error. Okay, so it's just a kind of a crude check, an intuitive check to make sure that you didn't do anything wrong. Okay, let's see if there's any questions in the chat. Nope, good. All right. Okay, now what's the maximum velocity? Same idea, but now you're going to look at equilibrium. At equilibrium, x is 0, and your energy is all 1/2 mv squared, but v in the middle is v max. Okay, and so there we have this formula. Okay, so E is equal to 1/2 mv max squared. Okay, and the 1/2 kx squared is 0. Okay, because x is equal to 0. And same thing, just rearrange. Okay, and then substitute in the numbers, and I get that it's 0.7174 meters per second. That makes sense because when you're out here at the end point, the velocity is 0. And as you come in, when you pass the 2.5 centimeter point, you're traveling at 0.5 meter per second. So by the time you get to equilibrium, you expect to be bigger than 0.5, and you are. You're 0.7174. Okay, and so let me explain that again. Okay, in case you missed the logic. When you're out here at the end point, you're at 0 velocity. When you get to the 2.5 centimeter point, you're at 0.5 meters per second. And you're only going to go faster from that point on. And so by the time you get to the middle, you're going to be going faster than 0.5. That number here has to be bigger than 0.5, and it is. It's 0.7. Okay? Great. Last question. So we'll finish on time. Last question is, how far from equilibrium? And when you ask how far from equilibrium, that means x is equal to, you're looking for x, okay? So how far from equilibrium is the oscillator when the velocity is 0.6 meters per second, okay? And so now I give you a v and I expect you to find an x, all right? And remember, if you have the energy at one point, it's the energy everywhere. And so now, because you're at a generic point, you can't use either the formula for A, or you can't use the formula for Vmax. You have to use the generic formula. There it is, highlighted. But you know E. E is this value right here because we calculated E. Okay? And so now just substitute in and see what you get. Okay? So we have all of the values, and for V, we're going to put in 0.6 now. You have all the values, and you're going to just solve for X. Okay, and so I'm going to go through them. It's 1/2 is 0.5, m is 0.15, v is 0.6 because I said that in, now we're looking at the point at which the velocity is 0.6 squared. Okay, 0.5, k is 43.35, and x, that's what we're solving for. Okay, and so just simplifying it, I find that x is equal to 0.01564 meters. Okay, but since we've been working in centimeters, I converted that to centimeters. It's 1.564 centimeters. Okay, and again, you ask yourself, does that make sense? Well, let's think about this. So when you're out here at maximum displacement at amplitude, the velocity is 0. When you pass the 2.5 centimeter point, you're at 0.5. Then you go faster, faster, faster. As you get to smaller x, you get the bigger v. At some point, bigger than 0.5 is 0.6, but that means that 0.6 has to be closer to equilibrium than 2.5. And so you expect an answer here which is less than 2.5, and it is. Okay. In other words, the bigger v is, the smaller x has to be. And so if your velocity is bigger than 0.5, then your x has to be smaller than 2.5, and there you go. It is. Okay. Again, just a crude check to make sure that you intuitively understand. I intuitively got the right answer. Okay, if you got an answer here that was like 3 centimeters, you know it's wrong because it has to be less than 2.5. Okay, again, when you're at 2.5, you're traveling at 0.5, but then as you go to smaller x's, you go to bigger. So when you get to 0.6 meters per second, you have to be at a smaller x than the 2.5 centimeter point. Okay, so there it is. That's all I was going to do today. And just to remind you, we're going to have a live stream on Monday and again on Wednesday. I'm going to redo some of the Newton's laws problem. Probably Monday will be um, Newton laws, and then Wednesday I'll do some more energy. Okay, probably Monday all Newton's laws. Wednesday a little bit of the Newtonian universal gravitational law, and then some more energy. Okay. All right, let me see if there's any questions in the chat. All right, looks like people are jumping out of the chat already. So I'll wait just a few seconds. No one had any questions. Let me just ask here. Any questions? So just typing this into the chat. Else, we're done. All right. All right, doesn't look like there's any questions. So let me just say goodbye. The reason I wave, by the way, is so that when I see myself waving, because there's a lag, I know that you guys have heard that I'm going to say goodbye. So I know it kind of looks a little cringy to see me saying goodbye like that, but that's why I'm doing it. The life of live streaming. Okay, we'll see you. Bye bye.